Yeah, welcome. So in this session, we are going to cover decision trees. Um, in the last class, we covered um, linear and logistic regression, and we also looked at the ways to evaluate model performance. We saw some basic ways of evaluating model performance. We talked about precision, recall, and all of that. Just basically a quick introduction to classical machine learning. So, in the session today, we are going to be covering decision trees. So, let me just put that there. And like we've been doing, we are going to firstly cover the idea, decision trees. We're going to be covering the idea behind decision trees, and we are going to come back to just see. We'll come back to this collab to see a quick implementation of decision trees using Sklearn. Now, decision trees is not really like linear regression or logistic regression where you have um, where it works for something alone. For example, this is what I mean. Linear regression, you know, from what we've covered, is just for regression problems. Problems where your target is continuous variables. While logistic regression is for situations where your target that is what you're trying to predict are categorical variables. But decision trees, this single algorithm, it has decision tree classifier and it also has decision trees regressor. So you can really use any one out of the two to get your job done. So if you have classification problems, you use decision tree classifier. If you have regression problem, you are going to use decision tree regressor. So we're going to be getting into that shortly. But firstly, let's understand how decision what decision trees is and how it works. So basically, decision tree is actually one of the um, foundational ideas in machine learning. In fact, some other algorithms that we are going to be looking at in the future are built on top of decision trees. They are built to make decision tree better. And now, what's decision tree? So decision tree is basically um, a machine learning algorithm that attempts to learn patterns in data sets by maximizing something called information gain. And let's firstly look at the layman idea behind it. So let's say we have, um, excuse me, perfect. So let's say we have um, around here. Okay, so let's say we have where is that? Excuse me, the board is not responding. I need to just delete that. Okay, I think it's taking a while to respond. Let's see if we are good now. And let's write here now. The board is still not responding in real time. But let's hope that that works. So let's say we have a data that is already projected on a chart. Let's say we have something like a chart that looks like this. Perfect. And that is a bit too large. Yeah. So, and it goes from the x axis to the y axis like that. And, we have 2 points on it. So let's say we have some red points. So let's say we have some red points around the one here. We have one here. So we have another here. We have, let's see, one here. And we have maybe one here. Then let's see another here. Here. Just to make it a little bit easy to be separated make it nicely separable so that what we are trying to explain is going to make more sense. One, two, three, four, five, six, seven, eight, eight. Um, okay, hold on. I might have to do it differently. I want to get 10 of them. So I'm going to go, maybe let's go green first. Let me put the greens around here. So I can just put the other ones inside it. So I'm going to have some green here, some green here, some green at this point. Let's see one here, some one here. Then I can have some at the extreme here also. So that way, greens are at the extreme. One, two, three, four, five, six, seven, eight, nine. Then we can have one last green here. Then for red, good, we can just have red in between these places here. Right, so maybe one, two, three, four, five, six, seven. Then we can go eight, maybe nine. One, two, three, four, five, six, seven, eight, nine, then 10. Great. So, let's say you can think of this as a data set. So, there's a data set and there is X1 and there is X2, you know. So, around here, let's say this is our X1, and on the on the horizontal axis, we're going to have our X2. So, you can think of it as, for example, if we should actually label these points, let me get maybe black. So, if we label this point, you can go 1, 2, that's going to be -1, -2, and -3. Then we can go here also, we can go -1, -2 here, and we can go 1, we can go 2, we can go 3, we can go 1, go 2, and 3. Yeah, that is perfect. So so you can think of this particular point here as something like maybe 2.1 on the y-axis, on the x1 axis, comma, if we drop this down, maybe 0.8 on the x2 axis. So it is something you can actually fill up in here, right? So this is to just show you that everything that we have as points here, they are like data sets here that we've projected onto this um, plane. Now, what we now want to do is we want to actually learn some pattern in this data set. And I hope this particular um, projection, this particular axis here is not going to confuse you. But let's just get into it. So let's say we want to now begin to learn some things. And how does decision tree do it? The way it happens inside decision tree, it is not like um, logistic regression or linear regression that you've seen. The way things happen here is we're going to have a kind of a tree structure that we're going to be learning from, and we're just going to be making decisions, like we're going to be making binary splits as we go down. This is what I mean. So we could start from, let me put that, let me remove this x1, x2, since we already have the idea of what's happening there. So we can come here and say we are going to draw a circle like this. That is a little too big, so I can just draw a smaller one. Now this circle here, we are going to call it a node. It is called a node, and this is actually the root node. This is called the root node, the first node, right? The root node. So we are going to start making decisions, and at this root node here, we are saying everything that we have, right? They are equal. What do I mean by that? This is what I mean. All of our red balls, we have 10 red balls. One, two, three, four, five, six, seven. Or we could just, to save ourselves the stress, we can just say 10 reds, and we also have 10 greens. That is at the point of making decision on the root node. This is the root node. The first split that we are going to do, there is nothing that we know yet, right? So we want to make our split. So we can come into this data and learn, as humans, forget about machine for now. As humans, how best can I firstly just split this in a way that I'm going to get some clean split? I could go something like I could draw a line around here. If I should draw a line around here, well, it is going to pick this red also, right? And if I should draw a line around it, I think that gives me this very clean split where I have one, two, three, four, five. So I'm going to have five green properly separated if I should put it here. So I'm going to say X, I'm going to say at the point where X is less than or equal to, what's that? 3. That is X1. No, that is X2. X2 is on the horizontal axis. So that's going to be X2. So this is X2 less than or equals to 3. Let me write that properly so it makes more sense. X2 less than or equals to 3. So if we should draw two lines like this, inside this X2 equals to 3. So let me draw the line of X2 less than or equals to 3. Let me draw that with a maybe purple. Purple. That's going to be this line here that goes like this and goes over 3 like this. And it means that we've separated this and everything here, 1, 2, 3, 4, 5, they are going to belong to a particular node, and every other thing are going to belong to a particular node. So it means everything that is true, and we can also come here and have our second node here. So for x2 less than or equals to 3, let's just say this is our yes side, this is our no side. So x2 less than or equals to 3, how many things do we have there? Well, we have all of this. And the other side is greater than 3, we have all of this. So on the greater than 3 part, we have 5, you can say 5 green balls, 5 green balls, then 0 red balls. Then here, what are we going to have? We are going to have 10 red balls, 10 red, and we're going to have how many greens? 5 greens. And what we've been able to do is, well, we've been able to get a pure split in this case. So we don't need to split this any further. Like we've gotten a perfect clean split on this side. So we leave this place alone like this. And this place is called a leaf node because the last thing that you find on this area is actually a split outcome. But this place here is going to be called a decision node because we still have a decision to make. We can still further split this, right? Because they are what? 5 greens, 10 red. So what we are left with here, 5 greens, 10 red. We need to look for a way of properly splitting again. Let's try and split again. So if we should come and make a split around here, let's get another blue line and make a split at x 2. If we say at x2 less than or equals to 0 here, like this, at this area here. So at this line here, at x2 less than or equals to 0, we are going to capture all these guys here, all these guys here, these guys. So that's how many red balls? 1, 2, 3, 4, 5, 6. So we are going to come here and say split this into 2 further, and the split decision is going to be x2 less than or equals to 0. So all of the force will be on this side. So it means we have let's capture the truth first. That is the things that are on the other side, which are the x2 greater than or equals to 0. So one, two, three, four, five, six. Six red balls. So we're going to say on this side, let me make that smaller so you can see. On this side, we're going to have six red balls. Um, six red balls. But let me actually make that red so that when we start computing, it's going to make sense. So six red balls. Do we have any green? Nope, we don't have any green. So I can say zero green balls. Excuse me. We have zero green balls. Then on this other side here, we're going to have how many is that? So six red balls, we are left with four red balls. So here we're going to say four red. That's not red. Four red. And how many green? We're going to be left with five greens, which are all of the greens that came from the top here. So again, we have a pure node here because it is only six red. There are no greens here. We can keep splitting this and splitting it till we have, for example, the next split that we could do is have this. We could put one here and it, takes out our grain for this. So it is going to further split grain where we have three grains and the only grains that are not accounted for are going to be these two. And it could just go on and on and on like that. And from looking at this, you are already going to see that the more we split, at some point, we are going to have everything categorized the best way that they are supposed to be. Meaning that if a new data point should enter into this data set, like if this is a model, right? It's a dictionary model. So let's say it enters into a data is shown to this model and the data happens around there at x1 equals to 2. And let's say at x1 equals 2 and x2 equals 4, which is around this at x1 equals 2, x equals 4, around this place. 2 comma 4 here. 2 comma 4. So let's say 4 is around there. So we already know that that is going to be a green ball. Why? Because we've seen that if we put it here, it does not satisfy the criteria. But if we put it here, it satisfies the criteria. And all of the stuffs there, they are green balls. So basically, that's what happens. And as human, it makes sense to you because, I mean, if you've been following what I've been doing, then it should make sense to you. But then, how does the computer do this? Like, how does the computer understand this? And that is where the machine learning aspect comes in because you might be thinking about this for people that, if you actually have a good grasp of Python basics, you might actually look at this and say, well, this is kind of like conditionals, right? Like nested ifs, if you know what that is. So it's like you're saying if x is less than this, do this. If it is less than this, else, like if x is less than this, do this, else do this other thing. Then inside the first if, you are putting another if inside it. Then that if has another if and else, and inside the else, nested ifs like that. And with what we've done here, the way we've structured it, that might work. You might say, well, a conditioner will basically fit it, but fix it. But then that might not be totally true because one, real life data set is large, like very, very large. You already know that. Apart from that, even on this small data set that we have here, what is the guarantee that we have that this particular x2 less than or equals to 3 is the best possible split that we could have done in this first instance here? What's the guarantee that this one that follows is also the best one to do? So that is where the ML part comes in. So the way the model does it is it actually splits, it goes into this place and performs every possible split possible, then takes the one that actually maximizes information gain, right? So it performs multiple splits across board, like a lot of splits based on all of the different attributes that we have, all of the different features that we have, and takes the one that possesses the most quality, that is, that results in the highest information gain. And what is information gain, right? There's actually a simple math behind that. Let me put that around here. So basically, the whole thing, the way that um, the system knows the appropriate split to take is by actually computing this. So it's going to say information gain, that is going to be entropy, sorry, yeah, that's correct. Entropy of the parent minus summation of, wi, which is the weight. You're going to see what that means shortly. Wi multiplied by the entropy of the child, right? So this is basically the sum of the product of wi, and wi is actually the size of the child with respect to the parent multiplied by the entropy of the child. So what is entropy? So entropy is one of the criterions that we use to evaluate, that we use to train a decision tree. And how does that work? Basically, entropy is a measure of impurity, and entropy is not the only criterion. There is Gini, there is a lot of them like that. So, but what's entropy? Entropy is easier for us to use in this case. So, entropy, like I said earlier, is the measure of impurity, and it ranges between 0 and 1. And if something has perfect, that is, if something is pure, like for example, in this case, we have this is a pure node here, like clean, pure node. Entropy is going to be 0. And in this case, this is a perfectly impure node, and entropy is going to be 1, absolute 1. So how do we compute entropy? We're going to say entropy is going to be equal to summation of negative pi, where that is the probability of that particular class, log pi. So that it could be like log to the base 2. So let's see how that works. For example, let's say we have two decisions to make, right? We want to either we want to split this place here. I just want to show you like how all of these things work, right? So we want to split this node here. Let's say we want to start training. Earlier we just chose x2 less than or equals to 3 and we ran with it. But we are not confident that that is the decision that we should make. What if what will give us the best split, the best, absolute best possible split is not x2 less than or equals 3, is something else. Could be x1 greater than or equals to minus 2, which is going to be at this line, or maybe something at this line. It depends. So in real life, like the ML model is going to search through everything. It's going to check and take the one that maximizes information gain, this information gain here. So how does it do it? Firstly, let's do it ourselves now manually. So we want to consider two splits. Split number one is x2 less than or equals to 3. So I'm going to come here and remove the ones that we have done before. Or maybe I should just do this and take this and I think I can duplicate. Yeah, I can duplicate it. Great. So I'm going to put it around the top here. On the top, maybe here. Yeah. Let me make this bigger a bit. So what we have here is we have at that top we have a split. But instead of just going with this particular one alone, we are going to be going with 2. So let me remove this from inside here. So I'm going to write it outside actually. So it's going to be x2 less than or equals to 3. So let's go check another interesting split that we could have gone with. And you're going to assume that all of this, you're going to assume that we have not done a split before, right? Like you're going to assume that there is no split before. Now, how does that work? The way it's going to work is, let's say the new split I want to take is, which one is, let's say, um, okay, this here. Let's say the split I want to take is this one. So let me come here and draw the line. Let's say the split I want to take now is this one here, and like this, right? So and that is x2, same x2, less than or equals to minus 2. So I'm going to come here and say second split is going to be x2 less than or equals to minus 2. X2 less than or equals to minus 2. So we want to compare two splits. We want to compare split of x2 less than or equals to 3, which is what resulted in, okay, I need to remove this. Great. So the first split is what resulted in this one here, right? It resulted in 5 greens, 5 greens, 0 red. So let me add 0 red here. And the second one here, this second split here, let's see what it gives us. So that's the line that we draw. It gave us this 0 0 0, that is 3 greens. So we're going to say, let's just draw a line here. The second split gave us 3 greens, 0 red. And on this other side, I told you, you must assume now that we still have 10 10. So we remove 3 from green. We have 7 greens, 10 reds. So we have 7 greens, 10 reds, right? And whatever is happening here is wrong. This particular split gave us what? 5 greens, 10 red, not just 5 greens. So 5 greens here, 10 reds. And we look at both, we're going to get back 10 10. So if you add 3 plus 7, 10 greens, 0 plus 10, 10 reds, 5 plus 5, 10 greens. So perfect. This is now where the real work is, right? So, the model is not just going to do two, it's going to do several. And it's now going to use this formula here to compute which one of them to go for. But in our case, we're just going to evaluate just two of it, just two of them rather. So now, between these two, which one should we go for? We are going to go for the one that maximizes this particular information gain. So how do we compute that? The first thing I want to compute is, we want to compute the entropy here, right? The entropy at this point. So to compute the entropy at this point, how are we going to get that? We're going to say, we're going to use this formula that you have, and let's start computing. Or maybe we can just go to numpy and get our value out. But basically, for the first one, let us just write it out. For this first one here, the entropy is going to be, the entropy around there is going to be negative, green, which is 5 green. Yeah, 5 all over. The total here is 15 for the two, right? Log 5 over 15. Okay, let me move that to the top a little bit. 5 over 15. This is 5 over 15 minus negative red. We have 10 red, so 10 over 15 log 10 over 15. And all of this, let's just use base 2, log to base 2. So this one here, this particular value here, is going to give us the what should be the entropy here, and this one here. So let's do for this second one. That second one is going to be negative 5 over 5, which is going to be 1 log 5 over 5 minus negative 0 over 5, which you already know is going to be 0 log 0 over 5, which is going to be base 2. Right. So in these two here, these two here, compute what you see here, compute the entropy for x2 less than or equals to 3. That is the value that should be here and the value that should be here. And for the second one, which is going to be this one, we're going to have, let me write that. We're going to have, excuse me, that's going to be this. So we're going to have negative, 3, excuse me, negative 3 over 3 log 3 over 3 minus, what's that? The red here is going to be 0. So negative 0 over 3 log 0 over 3, which is going to be something like 1 also. Then which is going to be something like 0 also. Then for the second one, that is going to be, which is this one, it's going to be negative 7 over 17 log 7 over 17 minus negative 10 over 17 log 10 over 17. So for us to actually be quick, let us go to numpy and set up a function that we can use to quickly get all of these outputs. I don't want us to take too long. I can say import numpy as np. So we're going to define a function called get. You can do this by hand if you want, but I mean you already know Python, so I can say get entropy. And the way get entropy is going to work is it's going to take number of red, number of green, and they're both going to be integers. Then what we are now going to do is we're going to actually put in this logic in there. And what's the logic? Negative uh, um, green over total log green over total minus negative red over total log red over total. So we'll come here and say negative, and we can open a bracket and say green divided by green, or we can start off by saying total equals green plus red, and we can say negative that all over total, that is negative green. So we don't need this extra bracket anymore. So all over, sorry, excuse me, total. Let me zoom in a bit so you can see. So negative green divided by total, that's going to be multiplied by log, and that's going to be np dot log 2, this one, of green over total. So we could actually make that probability. So maybe come here and let's just write it like that. So that's going to be green over total. I really do not want us to do too much of repetition, but I also want to keep this as simple as possible so that you can follow. Then the other one is going to be red, right? So I can just come here and say output. So I can say output equals negative green over total log green over total. Then I can copy this whole thing, paste it here, and say This is going to be red. So Control D, we have red. That's going to be negative green over total multiplied by log 2 green over total minus negative red over total. So, and maybe I feel like this is cool. Right. So we can just come here and say return output, right? Then if we run that, we can come to this place and check for each one of them. The way we know if this get entropy is working is if we give it entropy of this one here. Let's start with something very obvious. So the entropy for this place should be like zero, like perfectly zero, and this one should be one, perfectly one. So if we come and say green, I'm sorry, red equals one, green equals one, output should be one. So if we run that, that's correct. It gives us one. If we say red, because like I told you, this is perfectly impure, so entropy is going to be one. So in this case, if we say green equals three, red equals zero, that should be zero. Uh, red equals zero, green equals three, and we run that. It says none. Why is that? Okay, I think it counted division by zero. Let's do this where we actually wrap the whole thing in a bracket and see if we wrap this in its own bracket and also wrap this in its own bracket. I'm guessing that is green over total, red over total. So we run that and see. I'm making some mistake somewhere because we should not be getting 0 over 0, right? Like we should not be dividing by 0 anyway. And the reason why we should not be dividing by 0 anyway is because our green, for example, total is red, green. So our total where we are doing division at every point is going to be um, some actual value, right? If I should flip this and go 3 and 0 here. Yeah, so there's something wrong somewhere. So green, which is let's say in this case 0 divided by 3, negative of that multiplied by np dot log 2 of this, right? Then minus red. I do not know where that division by 0 is coming up. Uh, we can actually do probability of red, probably let's say p of red. To make it cleaner, p of red is going to be red divided by total, and we can do p of red comma p of green. Then the other one is going to be green all over total. So here, instead of doing this, we can say negative p of green, negative p of green multiplied by log of p of green. Perfect. And this is going to be negative p of red, p of red. Then here we have p of red. So doing this alone should at least fix our problem a little bit. So we've done the division before we even come into this place. So that's just basically going to be some decimal value, some probability value multiplied by some log value, then like that. So if we do whatever comes out of this minus whatever comes out of this, right? So let's run that and give this another spin. Still have that error. I really do not know what is happening. Let's test out this logic. We are taking too much. This is just like a side thing that we are doing. So I don't know. Um, let's try. Let's come here and do np.log to base 2 for something like 3 divided by, which one is that? 3. 0. That's perfect. Log to the base 2 of 0 divided by 3. Oh, I think that might be the problem. Where 0 divided by 3 is 0. So we say np.log 2 of 0, and we have divided by 0. Let's quickly just Google search that and say log to the base 2 of 0. That's the first time I'm seeing something like that. So let's see why that is. Log to the base 2 of 0. Uh, what is the log base 2 of 0? Not that logarithm of base 0 doesn't exist. Oh, does not exist. Really? Yeah, that's interesting. So basically, let's come here, right? So, but the idea is, well, you could say, this is 0, right? So the idea is that the entropy of a pure node, like if the node is pure, the entropy is going to be 0. So we can actually make that into, let's say, an if statement in here that returns 0. Now, if we come here and we start plugging in each of these values, we come to this place and start plugging in each of these values, and all of these places where we have zeros, we just know that the values of the entropy there is 0. All these places where we have a pure node. So this is what I mean. If we come to this place and we go, excuse me, we come to where this place here, and we start filling in the values. So here, entropy for this is going to be 0. Then the entropy for this one is 1. We've seen that. Then the entropy for this one also is going to be 0. And the entropy for this one is yet to be computed. We are going to compute it now. And the entropy for this one, we're going to compute it now. So let's go get those two values. So we come here, the first one is 5 grains, 10 red. So we come here and say 5 grains and 10 red. So we run that. We have 0.918. So we come here and we add 0.918, and 7 greens, 10 red. 7 greens, 10 red. So here is 7 greens, 10 red. So we run that, get entropy of that, and 0.977. So we come here and say 0.977. Where are you? This place. So that's for this one. 0.977. Now that we have each of the entropies, don't forget, if you are still following this 0.918 and 0, they are the two entropies for x2, for that particular split of x2 less than or equals to 3, and the second one is the entropy for x2 less than or equals to -2, which is this one here. So the next thing we want to do is we want to assess which of the splits is better. Is it this one or the second one? What we have to do is come to this place and plug that into this particular formula here. So the entropy of the parent is 1, which is they both have the same parent. So 1. So we are going to say Ig, that is information gain, or let's put that around where, around there. So I'm going to say Ig of 1, that is information gain of the first one, is going to be equals to, don't forget the formula for information gain, entropy of parent, which is 1, yeah, 1, and that's going to be minus weight. What is our weight? Our weight is the size of the child. The size of this child, this is the first one we are computing, the size of this child relative to the parent. So what is the size of this child? That is all of the data points inside this child is 15, 5 and 10. So that's going to be 1 minus 5 over 10. That is our WI is 5 over 10 multiplied by, how are we multiplying it by? No, this is wrong. Not 5 over 10. No. 15 over 20 rather. 15 over 20. Sorry. 15 over 20. This WI is, like I said earlier, the size of the child. The child is 15, has 15 data points in it. The parent has 20. So 15 over 20 multiply by what? The entropy of the child. So what is the entropy of the child? The entropy of the child at that particular point is 0.918. Multiply by 0.918. Then we can just go in here, add a big square, and do for the second one. This is for the first one. Then go minus again. That's basically just going to be like the continuous subtraction minus the second one is going to be what? Um where are you? This one here. So that is 5, right? 5 over 20. That's going to be 5 over 20 multiplied by 0. So basically, all of this becomes 0, and the only thing that we need to compute is this one here. That is 15 over 20 multiplied by 0.918. And also, information gain of the second one, which is for this one, we know that all of these become 0 also. Then we're going to have what? We're going to have 1 minus, what is the size of the child? 17. 17 over 20 multiplied by what? 0.977. 0.977. So if we come to NumPy and just quickly compute that. So for the first one, that's going to be 1 minus, excuse me, 1 minus what? 15 over 20 multiplied by 0.918. So that's going to be 15 divided by 20, and that's going to be multiplied by 0.918. If that is correct, I think that is correct. So we can really just multiply this whole thing like this so that there is a big bracket for everything. So if we run that, what do we have? We have 0.3115, 0.3115. So IG1 is 0.3115. So this equals 0.3115. And this second one is going to be 17 over 20 multiplied by 0.977. 17 over 20, 0.977. Like this. Let's confirm that. 977. Yeah, that's true. So if we run that, we have 0.1695. So that second one is 0.96. No, not 9. 0.169. 169. 0.1695 basically. Now, and what is the goal If you remember, I said the goal is to choose the split that maximizes information gain. So what split is that? 0.3115 is greater than 0.1695. So we go with IG1, that is the split one, that is this particular x2 less than or equals to 3 is going to be the split that the model is going to go with. Let's say it only has two splits to consider. And common sense wise, for humans, it's easier for us to see it, right? Because x2 less than or equals to 3 gives us five pure green balls at a go. Like we have straight five green balls. Meanwhile, the second one gives us just three green balls, the second split. So that's the idea. And I need to point this out. In the event that we have perfect split, that we have a tie, sorry, we have two splits and there's a tie between the split, the model is going to just take one randomly. And that's one of the reasons why you need to set random state inside decision trees. Yeah. Another thing is decision tree is a greedy algorithm, so it is quite um the way it works is that our first split, the way our first split goes, our model relies so much on that. That is what is going to set the tone for the other thing. So it does not look back, like it does not go back and adjust, and it just keeps going like that. So it's a greedy algorithm. And also there's something called max depth, which is like the number of layers that this thing goes. And the way to think about it, the number of nodes after the root node. So for example, this one has a max depth of two. One, two. So the more max depth you allow this thing to have, especially on simple data set, the more it overfits the training data because it's just going to keep on splitting and splitting and splitting and splitting. So that is basically the idea behind decision trees. That took longer than I um, had planned. So in the next like 10 minutes, let's just look at how to implement it, how to use it on our own data set in Sklearn, with Sklearn, the implementation of decision trees in Sklearn. So I'm just going to delete all of this, and it is going to be very quick because we already know majority of what's going to be happening in here. So we're going to say import numpy as np, port pandas as pd from sklearn dot tree. We're going to import, let's just look at decision trees classifier. Yeah, I'm going to say port plotly dot express as px. Yeah, we're also going to say from sklearn dot model selection import train test split. Right. I think that okay, we need metrics. You see from sklearn dot metrics import. Let's just get classification report. So we are going to load our data, and the data is going to be a pre-trained a sample data from Plotly. So it's going to be the iris flower data set. So we come here and say data.head. We're going to have this still coming up. So this is the data set that we're going to be using. I want to use all of this to predict uh species, like what species this thing are. And what we're going to do actually is we're going to use the species ID. So we're going to actually drop the species, instead of having to encode and all of that. So this species ID is already helping us. So we're going to just drop this species here. So these species here, they are the thing that we want to predict, but then they've already been encoded into species ID. So all of the set, those are going to be one. Then some other ones are going to be some value. So if I just run data alone, can you see? So Virginica is 3, Setosa is 1. So we're going to be predicting the species ID. So great. That means if I'm going to be doing that, I have to also remove species from my x's. So I'm going to say, sorry, x equals data dot drop, and we are dropping columns equals species, comma, species ID. And say y equals data species ID. Then after that, the next thing we want to do is we want to split the data set. So I'm going to say x underscore train, x underscore test, y underscore train, y underscore test equals train test split x comma y. Then um test size, that is going to be 0.2, excuse me, 0.2 random state is going to be 23. Then you should say stratify equals y, so that it stratifies. I've explained that in the case that in the event that you have class imbalance, you're going to be getting split that corresponds to the distribution of the groups inside the y. So yeah, that's everything. Excuse me. So the next thing we want to do is we want to train the model. Let's just say train and evaluate. So we're going to say model equals decision tree classifier, and we're going to have random state for the reason that I said earlier is one of the things in case there's a tie in the information gain values. So the model is just going to take one, and you always want to be able to reproduce that particular thing. So let's say you reproduce, you rerun the whole thing. If you want to get the same output, it means the model must make the same decision that it made by itself when it had tie. So that is what you want to do. So random state equals 23. You can say model dot fit x underscore train y underscore train. Then you can do train pred as equals to model dot predict x train test pred model dot predict x test. Then we can print report. And how we're going to do that? We're going to do that by saying print f string train report. And we're going to put that on a new line and say classification report of y train, comma train pred. We've already seen this in the previous classes on how to get classification report, how to evaluate these things generally. So the next thing to do is to do come here and say control D, okay, change this to test. So if we run this, we're going to see the output here. And what is the output? We see that on the train set, the model overfitted. Why? Because the model is too complex for the data, right? The data is just about 120 rows in the of training. So it overfitted on it. And you can see that the precision of one of the classes, which is 2, is really low. The recall for the other classes also, for one of the classes also low. So one of the things you can do is actually play around with some hyperparameters, because decision tree has trainable hyperparameters, values that you can play with. One example of that is max depth. See max depth of 2, and you run that and run this again. Where is it? you are going to see that this has just went, you are not seeing 111 like you were seeing earlier across board. Another thing is that the value that you saw earlier that was 0.83 or thereabout has really, really improved. This one that was 0.80 has really, really improved also. And that is just by setting max depth equals 2. So we've stopped this from overfitting so much like it was doing earlier. So that is basically Sklearn's implementation of it. And majority of the things has been abstracted away from you. And yeah, that is how we implement decision trees in Python with Sklearn. So, and if you're interested in the regression also, it's the same thing around here. You just have model equals decision tree regressor. They take almost the same parameters apart from criterion, and you just fit the exact same way, train the exact same way, test the exact same way, and your evaluation metrics is going to be something like RMSE, root mean squared error. So that is that on decision trees. In the next class, we're going to be looking at random forests. And just like in this case, also, we're going to be looking at the intuition behind it. And we're also going to be looking at the skill and implementation of it. So thank you very much. See you in the next one.